Awesome. We are live. Hello, everybody. Great to be here with Grigore and Sreeram. Quick intro. I'm Kaido. I'm the general manager at EigenLabs. It's my absolute pleasure to have this X Space live with Grigore, the CEO of PySquare, and Sreeram, the CEO of EigenLayer, EigenCloud. So just to start, Gregor, why don't you start us off? Tell us a little bit about yourself to the audience who may be first time seeing you from the Eigen Cloud ecosystem. Give a little bit of background of what you've been cooking up and what is PySquare?
All right. Thank you for having me, first of all. Hi, everybody. I am Grigore Roșu. I am a professor of computer science at University of Illinois, Urbana-Champaign, where Sreeram Kannan also graduated from some time ago. My specialty is correctness and security and verifiability and programming languages. And I've been here since 2002. Previously, I was a research scientist at NASA working on the very same topics. I'm now also the CEO and the founder of PySquared, which is the company that we'll talk about and our partnership today. I'll go into more details as we dive into the technology, but maybe now we can also have Sreeram tell a few words about himself.
Yeah, sure. Why don't you give a quick intro to the PySquare community who's watching this live stream?
Yeah. Hey, hi everybody. I'm Sreeram. Started the EigenLayer project 4 years back. Used to be a professor, ran the UW Blockchain Research Lab. Before that, I used to work on genomics and AI at University of Washington and my postdoc at Stanford. Before which I did my PhD at Illinois Urbana-Champaign, where Grigore was a professor. So pleasure to interact with him in this different setting here. My PhD was in peer-to-peer wireless networks. So we were thinking about how you build wireless networks without any centralized infrastructure. And so, it's a pleasure to revisit all of those kinds of ideas in a completely different context of blockchains. So excited on what we're doing at EigenLayer, our partnership with Grigore and PySquare. So we would love to dive into some of those things today.
Awesome. Before we dive into the partnership announcements, like a personal question, I would love to ask you both. Very rare. I have host a space where two ex-professors who are also both entrepreneur, founder, building a team, building a product. How has that been? What's how's that transition been? What's the biggest thing you learned? What are the biggest challenges? I'd love to just hear more about you guys' journey there. Maybe Gregor, you can start again.
Yeah, I can start because I started the first company before Sreeram. I started runtime verification back in 2010, before blockchain was even a thing. And our mission was to bring correctness to mission critical software and companies like NASA, Boeing, Toyota. And the challenge back then was pretty much the same as the challenge now, which is how to explain complex technology to not only investors, but also people who want to use the technology in their everyday life. How can we hide the complexity of the technology behind the utility of that technology? How to explain it in simple terms so that my mother would use it, my wife would use it. Not because they are not technical, but because they don't want to be. They can understand if we make a big effort. But the challenge, for me at least, was always how to explain something complicated in metaphorically simple terms and to find the right analogies so that people would not be scared but attracted of the complex technology.
Awesome. And just Grigor is very, very humble. For folks who maybe don't know much about runtime verification, I would say it's probably one of the most influential and earliest security auditing company in the world, and especially in crypto. Since the start of Bitcoin is in 2008, runtime started in 2010, and I would say a lot of the best projects currently you use in crypto probably has Grigore's eyes on them at one point as well. So really excited to hear the story there. Sreeram?
Yeah, not just in crypto, right? Runtime has been a pioneer outside crypto, NASA, like all these different, heavy duty applications require formal verification. So one of the things they say is crypto is the harshest security environment you can deploy code into. It's kind of like insane, right? You have NASA and then some degen DeFi project on the other side, and like it's because it's you just deploy immutable code into like a system, and then it just needs to be correct, right? And just speaking to this, to the broader theme that Kaido laid out here as a journey from academics into entrepreneurship, I would say it's like it kind of like went through my own journey from primarily curiosity driven action to impact driven action. I think like over time, so as an academic, my driving kind of like value was innovation, invention, creativity, curiosity, right? So you want to find out new things and like how something works. You have that itch and you can't sleep if you don't know. So that's the curiosity driven journey that I started, and over time I learned that I could be curious about many things. And so what is the thing that you want to be most curious about? Whatever has the highest impact. And so it moved from, curiosity is always there, but it moved from just curiosity driven to, okay, I want to find things that have high impact, high utility to others. And so that journey kind of like, that's why I went from peer-to-peer wireless to I started working on genomics and AI to then kind of like figuring out that blockchains is one of these places where we sense, like, I talk about this a lot, that, blockchain is like the biggest upgrade to human civilization since the Constitution. So it's one of the things where I think we sense the impact that it can have, this technology can have on the world is enormous. And the talent provisioned into like crypto and blockchains was rather minuscule compared to, like, let's say, a genomics or AI. Everybody you meet today is probably working on AI. I mean, the three of us here included, right? So there's always something to do with AI. So that's true. But if crypto can upgrade human coordination and there is not enough talent provisioned into the space, it provides an asymmetric opportunity. So that's something that we sensed very early on. And as we were trying to do this, we said, okay, if it takes to go build a company, to go build a protocol, let me do it, right? We did not want to do it. We just wanted to have that impact. We went to these communities, Bitcoin, Ethereum, and said, hey, here's a protocol, you can just use it, but it doesn't work like that. So we had to I had to start this company to do that. One of the things I realized along the way is, a natural mode of an academic is to think about the future, right? A future state of the world. This kind of a world would be amazing. It'd be useful. It'd be interesting. But as an entrepreneur, it's equally important, or maybe even more important, to find a path from the world we are in, an incentive compatible path from the world we are in to the world you want to go to. In fact, most things get stuck, not because people don't know what a better world looks like, but because we don't or can't find a good path from the world we live in to the world we want to go to. And so this is one of the things that I've had to kind of learn to distill long-term like plans into short-term incentivizable action, right? That, you have this, it's crazy idea, you want to build humanity's coordination engine or something. But then how do you distill that into, just do restaking? It's just stake and you're going to get some more yield. Okay, that sounds simple. Let me do that. And then you go to services and say, hey, service, you can use the stake and build something interesting. And then you do that. Then you say, it's some of these services are critical and impactful, like verifiable AI and agents. And here are some simple tools that you can use. And then you ratchet up on this hierarchy. So that's been my biggest realization. Number one. I think number two would be, what people would call focus, right? So you hear this in startups a lot. They say you should focus on one thing. And if I don't understand something in my own way, I usually don't follow it. And so initially I didn't follow it. I was like doing many things. And one of the things, the and then one day I realized that basically a startup is a machine that converts linear input into exponential output. It has to convert linear input into exponential output. Otherwise, how can a small group of people go change the world? It's just not possible, right? So if you have to convert linear input into exponential output, and you have that's an exponential game, and a startup is an exponential game. And if you did find two exponential games, two things which are like amazing to do, what you should do is to pick the one with the bigger exponent and put all your energy into it. Don't split it. Don't split your energy into two things. Put all your energy into one thing, and then that'll go way faster. And so that's kind of like a driving heuristic. I had to learn that because as an academic, you don't need to. You're not playing an exponential game. You're playing a very curiosity-driven game of finding out new things and connections which are unexpected. And so I'd say those two learnings: finding an incentivized path, and second is focusing on the exponential game.
Amazing. Talk about stories, talk about the new things, talk about, focus. So, Sreeram, why don't you continue a little bit? What are you focusing now? Like, what are you building today? And then we'd love to hear more from Grigore as well. Like, what are you building today?
Yeah, I think we recently announced this rebranding to EigenCloud, and people are still kind of like figuring out what is this EigenCloud? Is it like Google Cloud? What is this thing, right? And we had a tagline. It says cloud scale programmability. You can program just like you program in the cloud, right? You should be able to write any program and then deploy it. So the cloud made it super easy. Any developer comes in, write a software, just deploy to like Amazon or Google, and then it runs everything for you. Cloud made this super simple, but you don't get trust or verifiability with it. So EigenCloud's goal is cloud scale programmability and crypto grade verifiability. You want things to be verifiable, trustworthy, like you would do in the rest of crypto, but as easy, as scalable as the cloud. So that's kind of the overarching idea. And EigenCloud is an umbrella brand. It lends, clarity to what we have been doing and was maybe not clear to people. At the base level of a cloud is a data center, right? So you throw computation, and there's a data center where there are computers which runs the computation. We can't do that being in crypto. It's a centralized approach. What we do is at the base level, we have decentralized verifiable computation happening by stakers and operators. So that's EigenLayer is the base layer of EigenCloud. So you get stake. Anybody can put in stake and keep the computation running through a group of operators. So that's the core base level of EigenLayer. And once you have this base level, just like Amazon has a data center, EigenCloud has EigenLayer, on top of which we've built two critical services. One is a data service, EigenDA. EigenDA is a data availability service which guarantees that your data is verifiable and available. So you put the data there, anybody should be able to download and view the data. And it's a very important property, because if you guarantee this property, then you can take downstream actions depending on that. So that's EigenDA, which we had already built before we announced the EigenCloud branding. And it's the fastest data availability protocol and the most secured data availability protocol in crypto. It secures, $2+ billion of TVL built on rollups on top. So that's EigenDA. And then we have a new functionality coming up called EigenCompute, which is a computation service where you can take a container and then execute the computation of the container correctly, then bring the results on chain. So EigenLayer, the foundation, just like a data center, but distributed, decentralized, verifiable. EigenDA is verifiable data. EigenCompute is verifiable compute. These form some core elements using which you can build highly expressive applications on various chains. So that's the kind of like base level of EigenCloud.
And Grigore, before I pass it to you about FastSet, Pi Square, how does anything you're building relates to the different concepts Sreeram was talking about? Maybe after your description, we'd love to hear about the connectivity part as well.
Well, so it definitely relates both on the computational level and on the data availability layer, because essentially what we do and what I've done all my career was to reduce computation to mathematics, computation to mathematical proof. There is folklore in our domain. I teach programming languages, and one of the first lessons that we tell our students is that computation is deduction, but not only in theory. We developed frameworks like the K framework, for example, which literally does that. It takes a programming language and allows people to define a mathematical theory that describes in the most rigorous possible way known what the language does. And that means that you can take now programs in that language, and when you execute them, you actually generate completely automatically and very efficiently a mathematical proof, a very rigorous mathematical proof, going all the way down to the axioms of reasoning, of logic, of thinking. So computation is literally deduction, mathematical reasoning. And knowing that, now the next step is how to verify computation. Well, we just have to verify mathematical proofs now, which, believe it or not, is actually much, 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 much simpler than verifying an arbitrary computation in some arbitrary programming language or VM. Because the programming languages and VMs are very, they are moving targets. Any language worth its salt evolves. We have a new version every 2-3 months. Even the best languages out there, like LLVM, which, by the way, was also invented in our department, that Sreeram and I, affiliated with UIUC. But so even LLVM, right? We have a new version every 2-3 months. So that's the nature of the beast in languages. So instead of hardwiring an entire infrastructure around one particular language, what we decided to do was to hardwire the entire infrastructure around mathematics, which is the same and doesn't change. Okay, so now we take any programming language or any VM and any program in that programming language or VM and reduce it to mathematics. So very, very sharp separation of concerns. Computation goes into mathematical proof, and now verifiability goes to verifying mathematical proofs, which once you can generate the mathematical proof, that's the hard part now, generate the mathematical proof. But thanks to 50 years of research, not only in my lab, but around the world, now we have tools to do that automatically for us. But now, once we have the mathematical proofs, to verify the mathematical proofs, the problem is a lot simpler. And this is what we've been doing as a company from Pi Square from day one, which is proof of proof. That's where the name comes from, cryptographic proof of mathematical proof. So computation equals proof. That's the first proof, the first pi in Pi Squared. And then verifiability using the highest cryptographic primitives that we know, zero knowledge proofs. Those apply now to mathematical proofs. And we get a cryptographic proof that the mathematical proof exists and is correct. Therefore, the claim that has been made is correct. You see, it looks like a longer path, but it is reduced to something we understand very well and we have tools for, which is mathematical proofs. And now you ask how this relates to what Sreeram talked about, and I think there is a marriage made in heaven here, right? Because what EigenCloud does, both with respect to data and computability, reduces to verifiability in the end. But verifiability is such a broad concept. Now we make it very concrete. Verifiability of mathematics. And we know how to reduce everything to mathematics. And I can explain that even to my mother, right? So if something is true, it must have a mathematical proof. Otherwise, why should I trust it if it cannot have a mathematical proof, right? So now if it has a mathematical proof, we know what to do from here on in terms of verifiability. So that's how it relates to. gave you a longer answer than than we expected, but that's the
No,
answer.
that was awesome. How does, thinking about mathematical proofs, and the K language, and also thinking about verifiability landed you with FastSet?
Well, so once we had this pi-squared technique implemented, right, where we could associate to any claim that is true a cryptographic proof, a cryptographic certificate that attests for the correctness of the claim. The next question is what to do with it, right? So you have a claim, which is a sequence of bits, and then you have another sequence of bits, which is the proof of the claim. And with verifiers, you link these two together, right? And the proof is very, very succinct. So you know that the claim is true because of this proof. One metaphor here could be, imagine that God signs everything that is true, right? So you now have God's signature that something is true. Okay, good, right? And now what? What to do with that claim? We have to settle it, and we have to compose these claims, right? And this is actually where EigenDA also comes into the picture in our partnership. I'm getting slowly into that direction. The problem is that settlement on blockchains, and now I may say some things that are not very popular, but we implemented a layer 2 ourselves. We called it the VLM, the verifiable language machine, which was essentially K wrapped with cryptographic primitives into a blockchain, into a layer 2. And you could essentially plug and play your language. You want to write smart contracts in Python? All right, just bring the semantics of Python, which we had. Now upload it using MetaMask, sign the transaction, and now you have Python, which means that now you can write Python smart contracts. Wonderful, right? But we hit the same wall like many others. Performance. It was too slow in the end. And not necessarily because of K, because by the way, K is pretty fast now. On EVM is as fast as get. That's not the problem. It's not the performance of the computation, but the performance of all the synchronization and all the agreement between what should go first, what should go next, right? In blocks, in transactions. Again, metaphorically, one example that I give to people who are not necessarily very technical, but I can hope also use it here. Hope you don't mind, guys, because I know you understand the technology very well. But imagine that you have like 1,000 people on one side of a football field, and you want them to cross, the football field all the way to the other side, right? This could be amazing athletes, doesn't matter. But now suppose that you have in the middle of the football field a door that only one person can go through that door at a time, right? And you have to go all the 1,000 people through that door on the other side of the football field, right? No matter how well trained they are, it will be a slowdown. No matter how well synchronized they are, how you sequence them, there will be a slowdown no matter what you do. And then that was one observation, right? That everything is bottlenecked through that door, this tyranny of total ordering, of sequentiality. But that would not be too bad if it were really needed, absolutely needed. But we realized that more than 90%, actually 93%, we looked at all the transactions on Ethereum. 93% of all the transactions on Ethereum actually do not need a total order. Okay, payments, for example. If Alice pays Bob, Bob pays Charlie, Charlie pays Alice, and so on and so forth, millions of payments at the same time, they do not need a total order. Okay, voting. When we vote, right, does it matter that you vote before me or I vote before you? Not really. Or auctions. There are only certain constraints, global constraints, but the total order is not necessary. Yet everybody pays the price of the total order. And at some point, we decided to not be afraid anymore, to just say it bluntly, that blockchains are slow. And they are not necessarily the ultimate answer to the Web3 quest. We all agree that we need to own assets. Nobody should stay between us and our assets. It should be a peer-to-peer transfer network. And yes, blockchains fulfill that, but they are not always needed. And then we decided to, and that being said, actually, there are several modern blockchain implementations that take that into account, and they implement massively parallel execution engines. But in the end, those are optimizations. They are not the nature of the beast. They optimize the otherwise sequential semantics of the blockchain. And we decided to try something else. We decided to push parallelism to extreme. We decided to try decentralization and verifiability in the context of ultimate parallelism. No constraints on total ordering. It is your responsibility as an application to make sure that your transactions are we call them weakly independent, meaning that they can be permuted, and the different accounts should not step on each other's toes. But it turns out that those 93% of cases and many others can actually be very nicely, at least mathematically speaking, organized in a protocol that we call FastSet, which simply pushes this idea of parallel settlement to extreme. Right? Every claim comes with its proof. Once it's true, you can settle it. And you don't care about the rest of the other claims or the order in which claims are to be settled. If you need an ordering, for example, in Uniswap, you need an ordering by the nature of the protocol. If you need an ordering, then you have to implement that ordering. And there are well-known techniques that we learn in concurrency 101 courses and distributed system courses, how to implement a list using a decentralized, completely decentralized network of replicas, and they are not too difficult. And there are templates to do that. And once you learn how to do that, you realize that you can have blockchains, app chains, layer 1, layer 2s, no difference between them. All of them implemented as smart contracts on top of such a massively parallel and decentralized network. So that's what we did with FastSet. We implemented this protocol, and that would be the second innovation that we have in PySquare. Same like you had 2D innovations, and then they merged together in EigenCloud. Same happened in our case. We came up with the protocol, and then we came up with this universal approach to computation based on proofs, universal proofs, just one circuit to rule all of them, all languages. And then we put them together into the FastSet network.
This is all very exciting to hear, but is this still like a theory, Grigore, or is it like already implemented? No. What result have you achieved?
Exactly. We already implemented it. We already implemented, and you can go and play with it at fastset.xyz. There is a wallet there. You are getting tokens, and you can experience the thrill of instant finality. So the current prototype, so the protocol theoretically is unlimited, right? You can hear theoretical TPS, maximum TPS in some blockchains to 100,000, 200,000, and so on. In our case, the theoretical TPS is unlimited. It's horizontally scalable. If you want more TPS, you add more validators to the network.
Just so like double click on that number. What was the peak number you guys achieved during the testing period?
So during the testing, the public network, right now, if you go to FastSet XYZ, it will be more than 100,000. I think we've seen 131,000. But internally, and we'll announce that officially in a week or so, internally, we reached more than 200,000 at this point. And this is just in a couple of months of experiments. Again,
you don't sound that excited by it. It's just like just another day at the labs for you.
Because it's unlimited. We want 1 million. I want 1 million TPS at launch.
Because I feel very much like in similar boats with you. That's why where the question come from. You just casually saying, yeah, our testnet runs 100,000 transactions per second. That's absolutely awesome. What is the finality number like there? Is it like you have to wait 5 seconds?
Right. So it's a different protocol that needs to be understood. There are no blocks. Okay, first of all, and no ordering. Each claim, each transaction is generated, verified, finalized, and settled completely independently and in parallel with all the others. Right, so it's a bit an unfair comparison with blockchains, and that's why I'm not super excited about 100,000 or 200,000, because this is just the beginning. The number can be, very, very high. And you asked about finality. So the finality is also independent, right? So if you make a payment to Sreeram, then that is completely independent of any payment that I make to others. So you don't have to wait for me. You don't have to wait for the block, right, to be scheduled. So basically, the finality is directly linked to the speed of a round trip message on the internet of where you are, right? And we approximate it to 100 milliseconds. So we say that the finality end to end is 100 milliseconds, but the actual finality, if you measure it on the validators themselves, is less than 1 millisecond, right, to process the actual claim. And on the network, we have a small network now, kind of local-ish. It's about 2-3 milliseconds, right? But once the validators will be spread all over the world, they have to talk to each other. That's another aspect. So that's why it depends only on your speed, on your local. So you should have a very good, network if you want very high, very low finality time.
That sounds really, really exciting. Sreeram, while you're listening to this, what do you think is, makes PySquare really special and a great partner for the EigenCloud?
Yeah, I think there are several things. One is EigenDA is built without finality. I think everybody else building a DA basically built it as a chain. Basically, they all built a chain. And we went to first principles, and then we saw, hey, you want DA, do DA, don't do all the other stuff that you don't need.
Thank you for that. Yes.
Because what we found is every time when you're doing a data availability claim, what in every chain, what happens is they lock the state, and there is a single proposer who controls the next state update. It's called a block proposer, leader, validator, whatever, some different terms. But a node that basically has to produce the next block is a single point bottleneck into the entire system, into the entire speed at which anything can be done. And so when we built EigenDA, we obsessed about this fact that there should be no single point bottleneck. If there's a single point bottleneck, you're as fast as that node. You're not going to be as fast as, you're not going to support the internet's throughput. So we said EigenDA, and we were building this for Ethereum rollups, right? So you're a rollup on Ethereum, you're settling on Ethereum, everything. And so if you're settling on Ethereum, why should you also have your own finalization and a chain? And so we created a totally parallelized lock-free DA, but it doesn't do its own ordering. So it's an ordering-free DA. Okay. So we did this because we go to first principles, right? So it's because somebody is building a chain, we don't build a chain. We build what is needed. We built DA to be, and this is one of the reasons EigenDA is hyperscale. It's high performance, but it's specifically horizontally scaled, right? So anybody can come in, they have their blob to write to EigenDA, they encode it and directly open the connection and send the data to the nodes. Once they get a receipt, exactly similar to what Grigore said, one round trip on the internet, send, everybody got their chunk, get this signature, you got a DA receipt. Nothing else going on. Exact single round trip mechanism. And so this made EigenDA lock-free, parallelized, infinitely scalable. I wrote this ridiculous tweet like in 2022 February saying our goal is to achieve 1 terabyte per second. And, it sounds, because what I found is, the principles on which the Ethereum layer 2 roadmap was laid out was actually capable of handling this kind of throughput. It's just like stuck in some other engineering loop that they were not there. And so our goal we saw as EigenDA in the Ethereum ecosystem was to accelerate the data throughput. So EigenDA was built like this. And what I find with Grigore and like from where he started to like what he's done is do the similar thinking on complementary issues, right? So, EigenDA by itself doesn't give you like any kind of finality, but you may have an auction or something else that you're running where you need some kind of partial order. You need to know all the auction things have been put in, right? So then you go use PySquare and get all those receipts ordered, write to EigenDA in the backend, and you got your you got your auction done at the maximum possible throughput and the minimum latency. Normally what you think is there's a trade-off between these things. You try to push one thing, something else breaks, and this is one of those things where actually just better technology makes some things better, right? So 5G is just better than 1G in cell phones, right? It's just over time people figured out better things. It's kind of like that. So the two complementary pieces that I see with PySquare, first is like, how do you verify that the computation was done correctly? K and the formal semantics and this universal language machine, this kind of concepts all like dovetail into that. That it checks that the computation was done correctly. It can have this concept. In Ethereum, we talk about client diversity, right? Like many different clients can execute this. Grigore, how many different implementations of the K language are there? Like, I think formally verifying the K language, I think it's 30 plus different.
Oh, we have more than 30 programming languages formalized in the K framework. Yes. So and the K framework itself took many, many years, 20 plus, 22 years.
I'm talking about the verifier for K, like how many different, just the mathematical equations.
Oh, yeah. So yeah, if you're a student in my class, you'd have to implement one in your favorite language. I forgot their number. But the bottom line is the following. Mathematics is so easy to verify that you can write a proof checker for mathematical proofs, basically in a couple of hours in your favorite language, right? And then have coffee, your morning coffee.
See, this is like a very, very powerful idea, like, because exactly. I've written a lot of threads about client diversity in Ethereum. And one of the superpower is that you can actually run the same thing in different ways and make sure it's run correctly. And like Grigore is saying, it's math, right? And, it's also math simplified to like the base, like, oh, you only need these many operations, and then you can actually verify everything based on that. So it's a beautiful concept, and it has like massive client diversity. You have so many ways in which to verify it. So you can catch bugs and such really easily. And I was asking Grigore some time back about some of his experiments with rollups and running this kind of like fast verification. And he said, oh, we've helped the team. I don't know if you want to talk about the specific team here, but we help the team find bugs in their clients because we have a different way in which you verify.
Yes, really. Ethereum, they called it the K client at some point. We're one of the clients on Ethereum with the K framework. Yes.
Yeah, it's really beautiful complementary. I mean, these are not things we are doing at Eigen. So really exciting to see that. And the second one is this settlement or finalization with partial ordering. I think that's the FastSet algorithm. And again, the complementarity is really beautiful. So if you think about verifying computation, right, there are really two things going on. One is, if this piece of code runs, you get this answer. I think that's one verify computation. The other one is you want to protect against things like reorg or double signing. All the validators sign and give Grigore a block and give Kaido a different block, and then say, oh, this is block number 30, and tell both of you different answers. And this is not mathematically provable, just a priori, because I can just give you a signed block, which is correct. I can give you a different signed block, which is correct. In Grigore's block, I say I give Grigore $1 billion. And in Kaido's block, I say I give Kaido that same $1 billion. Both of them are like, okay, I got $1 billion. I can give my island to Sreeram. And now I got a private island and they got rugged, right? So this is a problem of double signing. And double signing cannot be protected mathematically or cryptographically. The only way to protect against double signing is crypto economically, which is the validators have put up a deposit and they are saying, hey, I'm not going to double sign blocks. I mean, if they run the correct plan, they're never going to double sign blocks. And if you did catch them red-handed, that they gave a different block to Grigore and Kaido, it's provable that they did this like bad thing. They can lose, maybe more than $1 billion because they've staked it on EigenLayer. Mm-hmm. So the stake in EigenLayer and the protection of reorg and settlement are like a matched pair. So you can actually use these two together and, a parallelized DA. So these pieces just fit in like a way that if we sat down and just constructed, we might still not come up with it, but it's such a good fit.
It's funny that once we solved that computational universality problem, and then we looked into settlement, right? We pretty quickly started running into the data problem. I was telling Kaido the other day that we could only have storage for 2 days of of running FastSet on all our network, internal computers, and everything. We put all the storage we had and all the money we could afford, and only 2 days. And I say, oops, this is a big problem. So we started writing down the requirements. What would be the requirements for the data storage, verifiability, parallelism, and so on. And guess what? They were exactly the requirements of EigenDA. So then why try anything else? Why re-implement? Why redo something that was done already really well? It's so interesting, right, to see the same concept actually being needed from 2 or 3 different places. When this happens, at least in science, each time I've seen that in my career, not many times, but each time I saw it in my career, that was a very major important concept, right? When it is discovered from different, there are classic examples in, for example, geometry and topology and algebra, right? The same mathematical result was invented in 3 different, apparently completely different domains. That only shows how critical and how important that concept is. And I think that was my revelation, right, with EigenDA. It was exactly what we needed.
That's absolutely awesome to hear. Specialization and coordination leads to stepwise progress changes. Before we leave some of the audience and I think we went pretty deep gigabrain, what are the 2 things you guys are most excited to see built on top of this partnership, either from the FastSet utilizing EigenCloud or from the Eigen side utilizing Pi-Square technologies? Maybe we can start with you, Sreeram. What is the 2 things that you're most excited to see?
I think fast auctions, right? So when you think about it, auctions are everywhere, right? Like finding price is like a base level primitive. And, auctions are needed to be fast in not just in the real world, but also inside blockchains itself. Like you can think of selling each block is an auction, right? So there's builder auctions, there's all these things. And so running auctions on like this kind of like a partnership, using FastSet and Eigen would be super exciting. So that's one like unlock that is immediate and of immense economic value, right? Because in an auction, if you can do censoring, right? So if you can control like what gets in and what doesn't get in, then you can exclude all the good bids and only keep your bad bids. And so you don't want to do that. And also, like if you can revert somebody thinks they win the auction, but then you revert it, then you get into trouble. So you need a lot of economic security for those things. So that's one thing I would say is immediate. The broader picture I just want to paint here is the one of the things, for example, in Solana, they talk a lot about is, there is a price of the transaction, or the cost to pay for the transaction depends on state contention. So if you're accessing a portion of the state or an app which is highly contended, only then your price rises. And I think what FastSet is doing is a generalization of this. So it's going beyond just, you're running everything in a single computer and parallelized. You can actually now run things on many parallel computers and scale your computation and parallelism quite a bit. So I do envision that lots of these, for example, lots of auctions happening in parallel, lots of, computations that need like finality, like all of them happening in parallel. And because they're highly consequential, I think those things are very well suited for this.
And those are very, very well doable right now. Actually, we worked out the details for auctions in our white paper. Actually, I just checked section 4.15. So if anybody is in auctions, you can see how they are done massively parallelly, embarrassingly parallelly in section 4.15. And also voting is in a similar category. And what is less known is that payments fall in the same category. So payments can be done embarrassingly parallelly. And now getting to my turn to say what I would like to see happening from our collaboration. I would say in the long term, it's hard to predict. In the long term, I think lots of amazing things will happen. But in the short term, what I would like to see is the missing peer-to-peer payment system. So Bitcoin promised us, peer-to-peer decentralized, verifiable, censorship-free payment system. And it is, but it's very slow. It's better characterized as a store of value today. And if we look at other blockchains, they are faster, but still not at that level of performance that we need as humans. If we really use Web3 for payments, then we need 100,000 TPS is too little, right? And if we take into account also all the agents and AI agents and micropayments they need, we quickly realize that even 1 million TPS is too little. So it should be unbounded TPS. And I think the technology is right here to do that, to have unlimited scalability payment systems with all the desirable features that we wanted to have, without even worrying about all programming languages, universality with VMs and with all the computational models and mathematical proofs and ZK proofs. Even putting all those aside, I think just a very simple payment system that we need and our AI agents need is still not there. And it can be done. I would really like to see that happening within a year or so. I think
that's awesome. Maybe we can even get it sooner, right? We have the Google announcement yesterday. We would love to see agents paying agents, and utilizing FastSet would be an amazing utilization of the technology. And that's it. I think we were just a little bit over time. Thank you everyone for tuning in today. And Gregory and Sreeram, thank you so much for your time. And give EigenCloud and also Pi Square a follow. And we'll continue doing great work, and can't wait to see this collaboration move even further. Thank you so much, everybody. Have a good one.
Bye-bye.
Thank you so much. Thank you, Grigore, Kaido.
Thank you, Sreeram. Thank you.